Okay, welcome to this video for Chem 161, looking at some additional details for Chapter 4. We'll look at some exceptions to our rules for octets and touch on bond order and bond strength as well. So it's known that there can be some exceptions to the octet rule, meaning that we can locate more than 8 electrons around an atom center and even under exceed that value, that is, satisfy a Lewis structure with less than 8 electrons around an atom center in a molecule. And this will happen depending on the size of the atom. There's also some situations where we can have an odd number of electrons to handle. So molecules that have an odd number of valence electrons will have at least one unpaired electron that will lead to the idea of what's called a free radical. So when we see a Lewis structure with just a single electron, we'll call that a free radical. Okay, so as an example for that, we can look at NO. Because nitrogen is in the 5th group, column 5 in the periodic table, we expect 5 valence electrons from that. And we've got oxygen, and here's 6 valence electrons from that. So we see automatically there that we have to build a Lewis structure with 11 valence electrons. And so therefore we've got our odd electron right there. Okay, so the Lewis structure here would be nitrogen tethered to oxygen, just use 2. Down to 9. Start with a more electronegative element. Just use another 6, down to 3, and those would locate on the nitrogen to complete the primary version, the preliminary Lewis structure that we still need to further consider. Clearly, the nitrogen does not have an octet at this point, and so we would consider borrowing a pair of electrons from oxygen to do that. Okay, so we'll consider this option here and still have that unpaired electron on the nitrogen in this case. So when we do this, we end up with a situation that minimizes formal charges, and we actually see a formal charge value here for the oxygen of 0, and likewise a formal charge here of 0 for that nitrogen. And clearly we've identified here this idea of an unpaired electron, and this is what we call a free radical. Okay, so you'll see this in certain molecules, and many are prevalent in atmospheric chemistry. Okay, very good. So the correct answer here is this right here. Okay, so that's an exception there where we have to handle unpaired electrons. Let's just make room for our next category. And we'll talk about incomplete octets. And so here we'll see these when the central atom is very small, like beryllium and boron. So reminding yourself of the periodic table, beryllium and boron are very early in the periodic table, and we can have compounds with those at the central feature. So we'll look at an example like BF3 to showcase that. So with 3 fluorines times 7 valence electrons, we've got 21 valence electrons from the fluorine contribution, and boron gives us 3 for a total of 24 to work with. Boron is the least electronegative of the set, so we'll put that in the middle, decorate that with 3 fluorine atoms. Just use 6 valence electrons, 18 remain, 2, 4, 6, 8, 10, 12, 14, 16, 18. And so that completes the valence count for the Lewis structure. Normally you would consider borrowing electrons from the outer element here, fluorine. First of all, fluorine's very electronegative, so that idea is kind of squashed from that. Further, the boron at center here is very small, and we'll see in towards the end of this video that when we consider putting a double bond in a certain spot here by borrowing electrons, we bring that bond to a shorter distance. So we're asking fluorine to come closer. Because boron is so small, because it's so early in the periodic table, this puts significant strain on that situation, and so we won't do that. So for boron and beryllium at the center of Lewis structures, we will simply break the octet rule, and crystallographic data and other measurements show that this is okay. So we'll simply satisfy the Lewis structure and have a correct Lewis structure where we have an exception here with only 6 valence electrons or 6 electrons near that boron, and we will not complete the octet. So this is the correct Lewis structure for that example. Okay, and some compounds, we're going to expand that valence shell and actually accommodate more than 8 electrons. For here, we're going to need central atoms that are quite large, so we're going to kind of see it around sulfur and up. So once we see sulfur and we go to larger elements in the periodic table, for the central feature of a molecule, that's where we're going to start to see exceptions permitted. Okay, so sulfur and up allows us to consider this. So let's just look at an example there in the molecule that is SF6. Okay, so 6 fluorines with 7 electrons each gives us a total of 42 valence electrons for that. Sulfur provides 6, so that's an additional 6. We have a valence structure, a valence count here of 48 electrons for our skeleton for the SF6 molecule. Sulfur in the middle. And as we try to just build our skeleton, automatically we see that we need 2 additional places for the additional fluorines. Because the sulfur is so large, we find it in the 3rd row here and down, we can add in extra fluorine spots. So we've automatically used 8, we've exceeded the octet with 8 electrons. We've now got 6 fluorines around there, each with 2 bonds, so 12 electrons are around the sulfur at this moment. Okay, and this is the correct structure to work with. We're down now to 36 valence electrons remaining, and we can decorate those fluorines finally. 2, 4, 6. 2, 4, 6. 2, 4, 6. So 6 each. And because there are 6 fluorines, 6 times 6, we're going to use up all 36 of these valence electrons. Okay, and if you went and ran your formal charges, each of these fluorines, which looks very much the same, would be a formal charge of 0. If you did the same here for sulfur, you would see formal charge is going to equal the 6 valence electrons minus half of all those in bonding circumstances, so that was 12. And we have no lone pairs, so that's a formal charge of 0 as well. So this is the correct Lewis structure for SF6, where we've exceeded or expanded the valence shell, taking advantage of d orbitals formally for that, and been able to accommodate well past the 8 electrons in the environment of the sulfur. Okay, so there's some examples. Takeaways there are for breaking the octet rule to lower values. We need very small central atoms like boron or beryllium, and if we're going to break the octet rule the other way and put more than 8 electrons at a central feature, that atom better be quite large, sulfur, and deeper in the periodic table. Okay, the next idea we want to touch on is what we can say about bonds based on all these structures. Okay, so we'll make room for that next topic here now. We'll take a look at an example here where we are asked to rank these molecules according to decreasing NO bond energy. Okay, so to help us with that, we will work with the Lewis structures and equate the type of bond, single, double, or triple, to bond energies. Okay, so let's begin by looking at the examples there and look at each of these to begin with. So the NO2 minus ion, a polyatomic ion with a single charge. Okay, so looking at this one now, NO2 minus, 5 valence electrons from the nitrogen, 12 from the 2 oxygens. We have an additional electron because of the charge. So this is going to give us 18 valence electrons to work with for the nitrite minus ion. 2 oxygen atoms. Just used 4 to build the skeleton. 14 to go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 2 more go on the central nitrogen. We've used all 14. And we now consider octets. So clearly the nitrogen in the middle is missing an octet. So we will borrow a pair of electrons. And here's where we might realize that we could borrow from the right or the left with equal probability. So we might expect some resonance for this nitrite polyatomic ion. So I'm expecting to need 2 or more answers at this point. And so one of which might look like this, where I borrowed a pair of electrons from the right oxygen, and this is now looking like an octet for the central nitrogen and octets everywhere else. Formal charges, -1 here, formal charge of 0 here, and a formal charge of 0 here. That's acceptable, and that reflects what we know for the nitrite ion. It should be overall negative, and we now position those brackets and that minus sign. Okay, this also means that there's another resonance structure where we show that double bond located to the other spot, so I'll just put that one above it. Okay, so we're expecting this to be in resonance with another option, and that's going to have the oxygen at left double bonded to the nitrogen instead. That'll put the formal charge of -1 on the right oxygen instead, and give us our second option. So there's the correct Lewis structures for the NO2 minus molecule, polyatomic ion. Okay, so we'll just make room for some of the other options. So good. Now let's consider the NO plus polyatomic ion. Okay, so NO, we have 5 valence electrons from nitrogen, 6 from oxygen. We have to remove 1 to provide positive charge, so we'll put a -1 on that. This will give us a total of 10 valence electrons to work with for the NO plus molecule. Okay, 10 valence electrons, we'll memorize that here. 10 valence electrons to work with. NO, I just used 2. I've got 8 left to use for this NO cation. 1, 2, 3, 4, 5, 6, 7, 8. That uses up all my valence electrons of the 10. They're all in this molecule. I clearly don't have an octet on my nitrogen, so I need to consider borrowing. Okay, so we'll try a borrow and look at what that looks like. Okay, oxygen is still satisfied at right, an octet there. A step in the right direction for the nitrogen, but we still do not have an octet. So we need to borrow yet again. So we'll establish a triple bond here. So this nitrogen will be 1, 2, 3-fold bonded to oxygen. We'll have a single lone pair on that oxygen and a similar situation on the nitrogen. So there's a bit of symmetry here if you think about cutting that triple bond in half, putting a mirror plane down that triple bond. When we look at this, we have octets now at both positions, so we've satisfied that rule. That is more important than formal charge rules. So formal charge here for the nitrogen will be 5 minus half of the 6 electrons in those bonding circumstances and minus the 2 for the lone pair. Formal charge here, 6 minus half of the 6 minus 2. And so you can see that the formal charge on the oxygen is going to be positive 1, and the formal charge on this nitrogen is 0. Okay, so even though we have a formal charge of oxygen that is in the positive, we've been able to establish the octets on the nitrogen, and that is more important. Okay, that if you check your rules for making those structures, that is more important than the formal charge trick. So this is the correct Lewis structure for the NO plus nitrosonium cation. Okay, and we'll just clean up some of this to make room for our last category to help answer this question. Looking at nitrate, NO3. Okay, so 3 times 6 for the contributions from oxygen. We have nitrogen providing 5 electrons, and we have the minus charge, and that's going to provide 1. So we've got 18 plus 6, 24 valence electrons to work with for this structure. Nitrogen in the middle, oxygen, oxygen, and oxygen. And we've used 6, so now 18 to go. 2, 4, 6, 2, 4, 6, that's 12, 2, 4, 6, there's our 18. All the electrons are in our structure, and now we need to satisfy the octet of the central atom. Nitrogen is missing one, so we consider borrowing a pair of electrons from one of the oxygens. So clearly, if you're getting used to resonance, we now know that we might expect 3 different options for the result here. Okay? So we'll make room for the 3 options that are the nitrate Lewis structures, and they're in resonance from one another. Okay, so one of them is going to be a double bond over here. Okay, all with a minus charge. That is in resonance with the next option, where we might have the double bond at the top. And the last option would be a double bond to the right position and single bonds to the remaining oxygens. Okay, minus charges on each of those 3 resonance structures for the nitrate. Okay. So in short, our answers are 3 resonance structures for the nitrate ion. We've got 1 here for the NO+, and we've got 2 resonance structures here. So if we think about the bonding to help us answer this question, speaking to bond energy, it might make sense to you that a triple bond is going to be much stronger than a single bond, given the extra electrons between the 2 atom centers tethering these atoms together. So triple bonds are stronger than double bonds, and those are stronger than single bonds. We also know that the bond length decreases. So as we kind of tether atoms together tighter with stronger bonds, a triple bond, we decrease the distance between the atoms. So this distance here is going to be the shortest of the series because we've got a triple bond. The single bonds are going to be the longest of the series. Okay. Now, to help us further, we have the idea of bond order. So we'll work with a bond order to help us, given that there's resonance at play. As we touched on in a previous video, if we have 1, 2, we have over in this area, we have 1, 2, 3 bonds that are at play across 2 different structures. We can predict that the average bond here is not a perfect double bond, but more of a 1.5 bond. So we can say that the bond order is those 3 bonds divided by the 2 structures. So this gives us a bond order of 1.5. Each of these bonds is 1.5. Okay? So that can help us. And if we imagine doing that for the nitrate option, we see that we have more just cleaning this up a little bit. Here we have 1, 2, 3, 4 bonds spread across 3 structures. So the bond order here is going to be 4 bonds divided by 3 different resonance structures. This is a 1.33 bond. So rather than this bond looking exclusively as a double bond, the other 2 Lewis structures make it look like a single bond sometimes, and that lowers its overall bond character on average to be more like a 1.33 bond instead of a single bond. Okay, so in short, we have a triple bond exclusively for the NO plus cation. For the nitrates, we have 1.33 bonds, and for the nitrite, we've got 1.5. So that is what we can use to help answer this question finally. Okay, so let's make some room for some of the next content here. Here you see our bond order equation that we've already established. So we'll just make some room here. Bond order was the number of bonds being shared across those resonance structures divided by the number of those correct resonance structures. So we saw that in those 2 examples of nitrite and nitrate. Okay. We saw, as a brief summary here, we have what we saw in those resonance structures. The NO plus had a distinct and perfect triple bond there. And because we had resonance, we had a double and a single. So this was more or less a 1.5 bond order, and the nitrate was a 1.3 bond order. So clearly the triple bond is the greater bond than the nitrite at 1.5 and greater than the nitrate at the 1.33. And so this helps us predict the bond energies. The triple bond's strongest, so that value should be the largest. Next would be the 1.5 bond at the nitrite, and the weakest bond energy, reflecting the 1.33 value here, is going to be the nitrate option there. Okay, so just to help us see that in the form of actual data, let's now show some of that. Okay. So our prediction was that when we have triple bonds, they will be the strongest and the shortest, And when we have single bonds, they will be the weakest and the longest. And so you will see that over lots of different data. So your textbook has a more complete set of data that we see here, but here's an example where we have carbon-carbon single, double, and triple bonds. So the triple bond should be the strongest. So it would take 839 kilojoules to break 1 mole of those bonds that are triple bonds. If I had 1 mole of double bonds, it takes 200 kilojoules less, on the order of 614 kilojoules to break 1 mole of double bonds in carbon. And the weakest is going to be the single bonds. Here, 348 kilojoules are needed to break 1 mole of those carbon-carbon single bonds. Clearly we were correct. As the bonds become, as they go from triple to double to single, the bond energy decreases. So our conclusions up here for this series were correct. Bond length, so we also see that if the triple bond is strongest, it should be the shortest. And so here in picometers, we see that as 120 picometers. Medium length for the double bond, and the longest is the single bond. Okay, and so we would be able to answer the above question to speak to bond length, provided we could calculate the bond orders like we've done already. Okay, and in a carbon-nitrogen series or even a carbon-oxygen series, we might expect to see the same thing. So let's look briefly at that. Triple bonds at the bottom there, largest number, medium, and small. And as far as length, triple bond should be the shortest, medium, and longest there. And we see it as well in the carbon-nitrogen series. And lastly, in the carbon-oxygen series, the longest bond, the medium, and the shortest bond, single, double, triple. And energy-wise, the CO bond is weakest on the single bond and strongest on the CO triple bond. Okay, so that is how we can address bond order to speak to both bond length and bond energy. And ultimately, our ideas for bond order came about by knowing the correct Lewis structures for molecules, even in the case when there is complex ideas like resonance. We were able to handle that and put an average number to help us there. And we opened earlier with some rules on exceptions for Lewis structures, and saw that the size of the central atom was a key idea there. And we also looked that we could even handle things like radicals where a single unpaired electron might result.